Go back to where we left off last time. This was on the board pretty much last time we met. But I just want to put it on there again to go over this part for laminar flow. We're looking at laminar flow over a flat plate. Laminar flow will occur, of course, we said, when the Reynolds number is less than 500,000. Two equations first we did previously. The first one gives us the velocity boundary layer thickness at any x value. The second one gives us the temperature or thermal boundary layer thickness at that x value. Ratio delta over delta T equal Prandtl to the 1/3. Then we went through and we found the local convection coefficient. Local means x at a particular x value. So here's the plate over here. If it's a laminar boundary layer and someone says, what's the local convection coefficient where my fingertip is? Put that x value in that equation and get h sub x. You can then define a Nusselt number, subscript x, h sub x. This is called the local convection coefficient. This is the local Nusselt number multiplied by x divided by k of the fluid. If you want to get the average value of h over the plate length L, then use this equation. HL bar, the bar means average. Average is this. And if you want to express it in dimensionless terms, then you've got the Nusselt equals 664 Reynolds to the 1/2 Prandtl to the 1/3, a dimensionless form of the equation. Okay, so that's where we left off last time. So as we mentioned last time, now we're going to look at turbulent flow. So turbulent flow, the Reynolds number is greater than 500,000. Here's the picture. Turbulent flow from x equals 0. If that's the case, this is the boundary layer thickness, delta. Very similar to laminar flow. The constant is different and the power of x is different. But turbulent flow, there's a lot of mixing that occurs. So it turns out that delta over delta T is 1 for turbulent flow. The velocity boundary layer thickness is about equal to the temperature or thermal boundary layer thickness. Laminar flow, that ratio was Prandtl to the 1/3. We solved the laminar flow equations. Pretty much it was done mathematically. When you get to turbulent flow, it's very complex, very difficult. It's not done mathematically. So we have to kind of walk our way through it. You start off, and from experiment, this is done experimentally, they found out this to be true. Now, CFX, go back to your fluid mechanics. This is the X means local, F means friction, C means coefficient. This is the local skin friction coefficient, dimensionless. 0.0592 Reynolds to the -1/5. Okay, experimental. Then they said, you know what? We had these two equations on the board a couple class meetings ago. The one is fluid mechanics, the other one is the thermal equation with temperature. These two equations are very similar, except the one in velocity has U, 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 temperature, T, T, T. They're very similar. Just replace the U by a T. And especially similar if alpha equal nu. Thermal diffusivity, kinematic viscosity. If that's true, the Prandtl number is equal to 1, since the Prandtl number is a ratio of those two. So these two equations look extremely similar for Prandtl number equal to 1. That leads to something called the Reynolds analogy. The textbook walks you through it in about a page. We're not going to spend the time for that page. We're going to the result. The Reynolds analogy result is, forget that guy now, Nusselt over Reynolds Prandtl equals CF over 2. This gives us the Nusselt number in terms of the friction coefficient. Where does that friction coefficient come from? Experiment here. They define a new dimensionless parameter. It's called the Stanton number, as I told you. There's a ton of dimensionless parameters in fluids and heat transfer. Stanton number. So this is called the Reynolds analogy. Take the results from experiment for friction and equate that to something to do with convection heat transfer, H. If you go through that on that page I mentioned, you end up with the Nusselt number is this, 0.0296 Reynolds to the 4/5 Prandtl to the 1/3. See, CF over 2. What's 0.0592 divided by 2? 0.0296. So you can walk your way through it that way. Where did this Prandtl number come from? Because we said it's 1? Well, yeah. The Reynolds analogy works out really good for Prandtl number equal to 1. What's a Prandtl number for at 300 K for air? 0.7. For water, 6 point something. So most fluids maybe don't have a Prandtl equal 1. So what do we do then if the Prandtl's not equal to 1? The author says we throw in a correction factor. So we put this guy on the end of it to correct for property variations, Prandtl to the 1/3. So this guy came by modifying this thing for property variations. Now it's good for Prandtl number from 0.6 to 60. Okay, so that's the range this equation is good for. What does that replace? Now here's a Nusselt, the local Nusselt number for turbulent flow. Here's the local Nusselt number for laminar flow. Okay, we got that guy boxed in. Okay. Now, for mixed flow. Mixed flow looks like this. So the flow starts out at the leading edge, x equals 0, as laminar. And then, as we go down the plate, if we get to the point where the Reynolds number is equal to 5 times 10 to the 5th, the flow transits to turbulent. That's called a mixed boundary layer, part laminar, part turbulent. Well, the same old thing. We want to find H. This is heat transfer class, so we want to find H. So H bar L, we have to get the integrated average value over the whole plate length L. The HX here is, of course, the laminar HX. The HX here is, of course, the turbulent HX. So you put this guy for HX, for turbulent, there, and you put over there the HX here, and you carry out the integration, and we jump down to the result. picture that 4/5 there. It results, when you're all done with the integration and clean it up, it results in that. Now, that A, he says, is a constant. What he's saying is that constant A depends on what the critical Reynolds number is for transition from laminar to turbulent. We use 500,000. The textbook for homework, for quizzes or exams, we use 500,000. But in the real world, it could be different. That 5 times 10 to the 5th depends on the approaching stream. It better be, you can see here, it can't be something like this. No, that flow is not going to transist at 500,000 if that's the approaching free stream. It has to be uniform. Streamlines are perfectly horizontal. Under all perfect conditions, then the critical Reynolds number is 5 times 10 to the 5th. So we don't need to worry about that in this class. The textbook always uses 5 times 10 to the 5th. That's okay. If it's not 5 times 10 to the 5th, then that A changes, and he tells you what to do in the textbook. But we're not concerned with that. In our case, A is 871. So we have Nusselt bar L equal H bar L over K. (0.37) Reynolds L to the 4/5 minus 871 Prandtl to the 1/3. That's how we get the average H for a mixed flow. Now, he also says if the flow is turbulent from the leading edge, then A equals 0. So we get this. So that is the average value of the Nusselt number, which is, of course, the average value of H, if the flow starts out turbulent from the leading edge. So these boxed equations on the board right now are added to these equations over here for laminar flow. Delta T, H sub x, H bar. Delta T, Hx, H bar. If it's mixed flow, H bar. The first thing you do in a problem, of course, is you find the Reynolds number at the end of the plate. Or you can find X sub C, but let's just say you find the Reynolds number at the end of the plate. If it's less than 5 times 10 to the 5th, you've got all laminar flow. Life is very straightforward. What do you want to find? I want to find the heat transfer over the whole plate. If the flow starts out turbulent from the leading edge, and I want to find the heat transfer from the plate, I need an H bar for turbulent flow. There it is. Put that H bar in here, end of problem. Got it. Now, the problem turns out mixed flow. Reynolds number at the end of the plate's turbulent, greater than 5 times 10 to the 5th. Find out what X sub C is. How do you find X sub C? Equate the Reynolds number to 500,000. Solve for X. That gives you X sub C. So if I want to find the heat transfer over the whole plate length, right here. There it is, H bar. Some people, I hate to mess this up, but they'll put an H bar subscript L. It gets to be too much in there, so H bar L. Where do you put the H bar? In here. Got it. If someone asks you, how much heat is transferred over the laminar part of this mixed flow from here to here? What do? Okay, I find H bar for the laminar boundary layer. Okay, there it is over there. Okay. What do I put in for L in that equation? Well, you don't put in L the plate length. You put the L where my right hand is. My right hand is where X sub C is. I put X sub C here. That gives me the H bar over the laminar part of the boundary layer. What if someone says, I want to find the local heat flux where X equal L over 2, where the black dot is. I want to find the local heat flux. Don't forget the word heat flux means Q double prime. Local heat flux. I need Hx, the local convection coefficient. I don't put the area in because it says heat flux. What if somebody says, I want to find the local heat flux at the end of the plate here? Fine. Where's my right hand? X equal L. Put L in there. Find H right here. Put L in there. There it is. Very simple. As I said before, once you get H, life becomes much easier. All the work is done in getting the right value of H. Q's fall out once you get to H, either him or him. Again, turbulent flow. Someone says, I want to find the local heat flux at X equal L over 2. Local, subscript X, right here. What do you put in for X? L over 2, got it. What do you do then? Put it in here and get the local heat flux. Sometimes you can put an X here. That just indicates at that particular X location. What's the difference in these two guys? How come he starts out turbulent from the leading edge, but he starts out laminar? Well, you've got to read the words real carefully. You won't find a totally laminar boundary layer a lot in the real world. It's hard to get. It's hard to get because the flow approaching the plate is not always as nice as you'd like it to be. So we had the problem. We worked in class a couple of class meetings ago. The tractor trailer truck with the trailer, and the problem said in words, it said, find the heat transfer, or find the temperature at the top of the truck, assuming the flow is turbulent from the leading edge of the trailer body. Okay, so he told you that. He said, assume it's turbulent boundary layer from the leading edge of the trailer body. If the problem says nothing like that, then you do it this way. Assume it starts out laminar. If you see the magic words in the problem, or an exam, that the flow starts out turbulent from the leading edge, you do this guy. So look for those words in the homework problems in the textbook, or in the exam or quiz, whatever. Look for those words. Okay, so 3 possibilities. All laminar on the plate, all turbulent on the plate, and a mixed flow. If I want to find the heat flux at that little point, I go to over there, and for X, I put in that point right there, that X value. Okay. Turbulent boundary layer, if I say, what's the local heat flux right here? Turbulent, local, right there. There it is, turbulent, local. So everything in Chapter 7, external flow, that is useful in solving problems is on the board right now. Laminar, all turbulent, mixed flow. Get the right value of H. Maybe find delta or delta T. Find the local H. Find the average H. Put them in the equations for Q. Q or Q double prime. That's it for a flat plate. We didn't draw this, but I drew a picture over there of how Hx varies with X. It goes down like that. For turbulent flow, it looks like this. It doesn't quite go down as steep. It's flatter. Laminar flow, Hx drops off more dramatically. Mixed flow, laminar boundary layer, picture over there. At that point, the flow transits to turbulent. Dramatic things happen. Turbulent flow, there's a lot of vertical mixing in the fluid. The vertical flow, laminar means lamina. Lamina means like paper in your notebook. They slide over one another very easily. So the molecules of the fluid slide over one another very easily. Turbulent flow, there's a vertical component of that velocity. So now it's rougher. There's more vertical mixing. That creates better heat transfer. So now, when you get to turbulent flow, bam, H sub x goes up dramatically. And now it follows that. So that's what happens in a mixed flow plate situation. Hx, really good near the front of the plate, really good, the best. Hx goes down until it reaches the critical x value. Now the flow transits to turbulent. Bam! The heat transfer goes up again. But now it declines at a more gradual rate in the turbulent part of the boundary layer. So that is why, again, if you want good heat transfer, you want turbulent flow. If you want good heat transfer, you want turbulent flow. If you want to reduce the drag on a body, then you want laminar flow. So fluid mechanics reduce the drag, I want laminar flow. Heat transfer, I want good heat transfer, I want turbulent flow. Just the opposite, fluids versus the heat transfer. Okay, so this is the first part of chapter 7, flow over external surfaces. Our next topic is going to be flow over cylinders. So it'll be flow not over flat plates, like pipes, cylinders, okay? So we'll do that next time. We're going to stop right now. One question, yeah. Is what? Oh, yeah. You would put this distance in this equation right here. That. Is that what you're thinking about? Now, tell me why you're concerned with that, because I think I know why. Tell me why you're concerned about that. Okay, I'll give you a major hint here. That's an approximation, because really, where does that turbulent boundary layer appear to have started? There. What distance should you have put in? This distance in that equation. But the textbook doesn't want to get that involved. You can do it that way. You've got to work backwards. But it's much more complex. And typically, here's why it doesn't matter too much. For most flow situations, here's what happens. There's laminar, there's turbulent. Now extend that turbulent boundary layer back to the plate. Ooh, it gets real close to there. So the air becomes minimal. But he says, I'm not going to make life complex for you. If somebody says, find the value of the heat flux here, and you're in the turbulent range, just take this value and put it in here, and you'll be close enough, okay? But you're not going to be correct, okay? That's a good question. Thank you.